So welcome everyone to the second session of day 4. And it's a great pleasure for us that we have Hridis with us. So Hridis is currently a faculty at IIT Bombay, and he has worked on many exciting topics in twisted bilayer graphene and topological superconductors. And he is also quite involved in thinking about new problems in Weyl semimetals, and he will tell us more about surface transport in Weyl semimetals. So I will give you a warning 5 minutes before the end of your talk, and if you want to, it's up to you if you want to take questions within the talk. Thanks. Please go ahead.
Okay. Thank you, Sayantan, for the gracious introduction. And I would also like to thank the organizers for sending this invite and giving this excellent opportunity to present about one of my recent works in Weyl semimetals. Okay, so how do I change it to, can you see my cursor?
Yes, I can see that. Yeah.
But how does one change it to pointer? Here, pointer options, laser pointer. Okay, perfect. Okay, so today I'm going to talk about transport in Weyl semimetals with the focus being on surface. So here is a quick outline of the talk. So in the beginning, I'll start with an introduction where I will sort of motivate why and how Weyl fermions appear in condensed matter physics, and what does it mean to say that these objects are topological. And I would also review very quickly what one typically means when one talks about transport in normal metals. Okay, so I apologize at the very outset, because this part is really very basic and introductory. Given the fact that this conference brings together people from 2 different disciplines, and there are quite a few graduate students, I thought it doesn't harm to get started with some basic stuff. I'm sure the experts in the audience might find this very trivial. Okay, so once I've gone through this part, then I will move on to transport in bulk of Weyl semimetals, both without magnetic field and with magnetic field. And here I will review some of the existing works which have dominated the landscape, let's say, over the last 10 years or so. And finally, I'll move on to transport on the surface of such materials, which is what I've been working together with my collaborator in the last couple of years. And I will show you how the surface also has some anomalous features, which I believe has been missed so far. And this will lead us to an interesting question where I will suggest that perhaps the surface of a Weyl semimetal is a novel correlated liquid. And then I'll finally summarize with the summary and hinting on some future ideas that one could pursue. Okay, so let's start with something very basic. So what do we typically do in condensed matter? So we know our basic idea is that when we have a single particle in free space, we know what quantum mechanics tells us. It's a plane wave with the dispersion energy going quadratically with momentum. So that's our standard parabolic dispersion for a free particle. Now in condensed matter, typically we deal with systems which are crystals. That is, there is a periodic lattice. So the electron will see a periodic array of potentials. And then Bloch's theorem tells us that, well, although we have so much scattering going on, at the end of the day, not much changes drastically, in the sense that the wave function retains its plane wave form, except that with a prefactor which modulates in real space with the same periodicity as the lattice. On the energy side, the dispersion changes to something new with a new index called n, which is called the band index. And what do we mean by it? So if we just take this parabolic spectrum and suppose that this periodic potential is very weak, then we can do a perturbation, and you can show that not much changes, except that at reciprocal lattice vectors, pi by 2 pi over a and 4 pi over a, in integral multiples of 2 pi over a gap opens up. and a little bit changes, but otherwise it's almost like the parabolic one. Now, because we are dealing with a periodic system, I can simply go to a representation where this momentum, instead of going from -infinity to +infinity, I just fold everything up, define k to be just -π/a to +π/a. And so you can see this stays as it is, this goes here, and you just keep folding. So the entire information here stays here. It's just that instead of going to the entire domain of momentum, you just define momentum within this small region called the first Brillouin zone, and then you have different branches of dispersion. So when we as condensed matter physicists call something called a band, it's nothing but it's different dispersions which are gapped at certain regions. Okay. Now, basic textbook tells us that when the Fermi level, so that is one part of the story. Now I have lots of particles which I need to put into this system, and as I fill them up, the last energy will be the Fermi level. And if it lies in the gap, then it's called an insulator. And if it is lying partially filled band, then it's called a metal. So that's our basic solid state 101. Okay, so in real life, of course, things are slightly more complicated, both in the fact that the periodic potential is not really weak, and also the real object is three-dimensional. So here is a simple example. Let's say copper, which is something that we encounter every day, right, in our wares. So what is this counterpart in this material? So here, because it's a three-dimensional object, the momentum space is also three-dimensional. And so all these indices X, W, L, these are just three-dimensional vectors in different directions in 3D space, which have been laid down on one axis. Okay, so these are really different directions. And as you can see, there are really bands, but they have rearranged drastically. Now we know copper is a metal, which means the Fermi level should lie inside a band, partially occupied band, and this is exactly what you see. Okay. Now it turns out that in certain materials, because of the crystal symmetry, graphene being the simplest example of that, which is a conglomeration of hexagonal arrangement of atoms, it turns out that at some value at the Fermi level, two bands touch, okay, they intersect. And not only do they touch, they also have a linear dispersion, which is very reminiscent of what we encounter as Dirac fermions in relativistic quantum mechanics. Let's move on from 2D to 3D. So continuing with the idea, here I'm giving you some real life examples. So as you can see, the real life bands are very messy. So fondly, these are called spaghettis. You can think of this as a spaghetti of bands. And this is, for example, a material called Na3Bi, which is three-dimensional. And if you zoom in near the Fermi level, you can see that this here also is intersecting in a linear way. Similarly, I give you another material, which is TAAS. And here also you see that at the Fermi level, the bands intersect linearly. So if I just schematically write it down here, the schematic picture, then you can see that this also has a Dirac form, but it is really now three-dimensional. And here it is as if this doubly degenerate, so these are all doubly degenerate bands. It is as if this doubly degenerate band has split along the momentum axis and has become singly without any degeneracy. Okay. So typically this is what is called a Dirac semimetal, and this is what is called a Weyl semimetal. Borrowing the nomenclature from relativistic quantum mechanics. Now you can ask me, well, I mean, if it is it really true that if I have any place where such intersections, linear dispersions exist, and there is band touching, should I be able to call them Dirac and Weyl? The answer is not really, because such intersections can happen anywhere. It's not really that uncommon. There are two requirements. One is it has to be near the Fermi level, because all perturbations we add to get some observable will involve particles near this Fermi level. So that intersection has to appear here. But more importantly, it really has to have the same emergent Lorentz symmetry that you encounter in relativistic quantum mechanics. By which I mean that going from momentum, let's say I change it to real space and put speed of light 1, we know that this is our massless Dirac equation in relativistic quantum mechanics. And if we take the Weyl representation, we can split this into, instead of a 4x4 bispinner, we can split it into a left-handed spinner and a right-handed spinner. So this is what relativistic quantum mechanics demands. So in condensed matter systems, we will call those materials as Weyl systems and Dirac systems, which near the Fermi level and near such dispersion will also obey the same emergent symmetry. Okay, so the wave function will have similarly a 4x4 component, which transforms like this, and a 2x2 component with left-handed and right-handed natures. Now, henceforth, I will not talk much about Dirac. I will entirely focus on Weyl systems. So just the last sentence about these Weyl systems in condensed matter is that in our solid state systems, we can slightly generalize this idea in the sense that these cones of handedness, that is chirality, they can come in multiples of 2 or 4. Okay, so they need not be just 2. Okay, they can come any number of cones as long as they are multiples of 2 or 4. Okay, and the other thing that we can typically happen is these cones need not lie at the same energy. So this is what I'm denoting by mu j here. The jth cone, it can be slightly up, this can be slightly down. And I've also denoted this with a generalized velocity so that the different directions can have different slopes, the cones, which means these can also be tilted. So this is the most generic situation in a condensed matter Weyl system. And the other point to appreciate is that whereas here, sigma really refers to the spin degree of freedom, when we write sigma here, this can of course be real spin, but it need not be. It can be some emergent internal degree of freedom, which we will call pseudospin. Okay. All right, good. So, so that is the basic idea of what I mean when I say there is a Weyl semimetal in our solid, in a certain solid. Now we all hear that there is something related to topology of the Weyl fermions. So what does it really mean? Well, the way at least I understand is that if you take the spinner of your Weyl system, you can define, excuse me, a Berry connection, which we are all familiar with from the last few talks that we have heard. Simply the overlap between two spinners very nearby in the K space. And then we can define a Berry curvature, which is nothing but a curl in your K space, in your momentum space. And then around each Weyl node, we can define the monopole charge, which is nothing but the total Berry flux coming out of some closed surface that you draw around this point. Now, it turns out that in your Weyl system, the chirality that we just saw before, your the spinners, which are eigenfunctions of your gamma 5 matrix, is identical to this object that we have just defined. And this object is an invariant because it really does not matter on the parameters here. I can change V, L, M, mu. It wouldn't matter as long as it is a Weyl spinner. It will give you either plus or minus 1. And each sign can be ascribed to a certain chirality. So here the cartoon is these two. Let's say we have just two nodes. Then in one part, the Berry flux is coming out. It's emanating from it. And the other part, it is actually getting in. Okay. Now there is this famous Nielsen-Denomia theorem, which says that there is no way that you can have an excess of chi. So however many nodes that you might have in your system, they have to come in pairs so that the total monopole charge or chirality has to go to 0. Okay. All right. So that's what typically what we mean by the statement that there is some topological significance of the bulk. Now, in solid state systems, you see we have real crystals that we're talking about, and its low energy theory is mimicking your relativistic quantum mechanics. But because it's a system that we can really hold in hand, we can also go to its surface. And it turns out that in these Weyl systems, the surface is a peculiar object. Why? Because on the surface, you can have open segments of isoenergy contours. What do I mean by it? So let's say I have just two Weyl nodes. One is plus chi, chi and one is minus 1 chi. If you just take this object, instead of having it infinite, you cut the surface on top, go to the top, calculate its wave function on the semi-infinite top plane, and now project it onto the surface Brillouin zone that is in its K space, but now it's two-dimensional. You can show that there exists states on the surface which are localized which start from one Weyl node and end to the other, but they do not form your typical closed loop that you would usually expect in a two-dimensional gas, for example, right? And these loops, these states are called Fermi arcs, and they are guaranteed by topology, okay? So before I get to the topology part, let me just explain in this picture what is happening. So the plus and the minus can be thought of as the two nodes in the bulk, and this line is on the top surface Brillouin zone, where only two momenta are now relevant, because the other side is not translationally invariant, you have cut it. And here is the arc. Now you can ask, so this is at the Fermi level 0, meaning the Fermi level, the bulk Fermi level is at the node, okay? Now what if you have your Fermi level slightly up? So then clearly in the bulk Weyl nodes, you will have little loops, and you can show that these Fermi arcs will connect these loops in such a way that they're tangential to the loops at the point that they touch, okay? Now, I made the comment that these arcs have to appear. There is no way you can get rid of it. And there is a topological reason. Why? The topological reason is as follows. Suppose I consider just two nodes, one of +1 and one of -1 chirality. So this, and call this direction Z direction, right? So as I've told you, this side is, let's say, giving out Berry flux, and this side is accepting Berry flux. So if I take planes on this kx-ky plane and consider the Chern number on a kx-ky plane, two-dimensional plane, as a parameter of kz. So I'm taking various planes and I'm going as a parameter of kz. Then inside the two Weyl nodes, because flux is coming out and entering here, you can see there is a net flux coming out of any plane, which means the Chern number is always going to be 1. But on this other side, the Chern number goes to 0, right? So, but we know from the bulk boundary correspondence that if we have a non-trivial Chern number in the bulk and it is gapped, it essentially means that the surface has to have topologically protected quantum Hall states, which are states that will lie localized on the surface, right? And that means that you are guaranteed to have some state on the surface between these two nodes, and this is exactly what the Fermi arcs are. And there is no way to get rid of it by any smooth transformation unless you completely kill the system by some strong perturbation. Okay, the last thing that is very important about these surface states, and which distinguishes it from a standard topological insulator, is the nature of its localization length. So I made the remark that these surface states are localized in the surface. So this is my humble attempt at drawing a cartoon. So these red lines are sort of denoting the length to which the state is going into the bulk. So here it's a hybrid picture. Suppose this is my Weyl bulk in the R space, and this is the top, but in the momentum space. Okay, so this is some Fermi arc state. Their localization length, if I think that this is the Z direction and it is localized, then the localization length lambda actually changes depending on kx and ky. And right at the Weyl point, they actually diverge, which means it leaks right into the bulk and appear on the other side. There is no way you can stop it. And this is understood because at the Weyl point, there is no gap in the bulk. And the localization length can be thought of as inverse to the gap, right? Compare this to a standard topological insulator where the bulk is completely gapped. So the surface state, which is similar in nature as this, will never leak completely into the bulk. It will always be localized on the surface. And that's a huge difference, as you will see when I'll talk about transport. So here I'm showing you a cartoon, but the bulk is not gapped at the Weyl node, but here at all points in the Brillouin zone, the bulk is gapped. So the surface state purely lies in the gap and is always localized. Okay, with that, now I hope you have some idea about the first two parts, which is what is a Weyl semimetal in the condensed matter context and what is so topological about it. Let me now round up the last part of this introduction, where I just want you to give the basics of transports in a condensed matter system so that we can compare this to the results later. So let's start with a very simple idea. Let's say I have a charged particle which is moving through a medium where there are lots of scatterers. These are, let's say, some impurities or disorder, right? So just classically, then the current is total density times the charge times the velocity. And the momentum of the charged particle is getting accelerated because of the electric force. Now, if I don't have the impurities, it will keep accelerating and go to infinity, right? So I have to have some damping, which I'm just phenomenologically putting by hand through some tau. Now, in a steady state, this will go to 0, and it will give me some V average, some average drift velocity that it will acquire. So I can then simply plug this back in, and this gives me a relation between current and electric field. And we know in linear response, if we restrict the response between current and electric field to linear order in the driving force, the field, then the coefficient here is nothing but the conductivity, right? Now, the conductivity, as you see, is proportional to tau, which makes sense. Tau is the mean value of the scattering time. If the scattering is very weak, so the tau is large, conductivity is large, and vice versa, right? Now, typically in experiment, what you measure is the resistivity, which is the inverse. So the resistivity will go as 1 over tau. And it usually increases with temperature in a metal. Why? Because in a metal, there is no dearth of carriers. There's a lot of N. So with temperature, N really does not change much. What really changes is the scattering. So as you increase temperature, the scattering time decreases. There is more scattering. So this increases, and rho typically increases with temperature. So the only thing that I want you to remember going ahead is this, that the conductivity or the resistivity has to depend on tau, and it typically increases with temperature because of this dependence in tau. Now, the actual scaling here will, of course, depend on your microscopic details, but let's not get into that. Okay, that was just in an electric field, a very nice classical picture. What about a magnetic field? Again, if you have an electric and a magnetic field, let's say I have a magnetic field here, I have some electric field here, then it's the same idea. On top of the electric force, I have some Lorentz force, which is acting perpendicular to it. And again, I kill the drift by some phenomenological scattering time. And once you solve this and plug it back into your expression for J, you can immediately show that the conductivity will now have 3 different components, right? Because you have broken the similarity in the different directions with the field now, with the magnetic field. Now, it's easy to show, it's just 2-line calculation, that the diagonal part of the conductivity, that is along the field, electric field, the current will be given by this. Sigma naught is your Drude conductivity that I just showed here. This is called the Drude conductivity. There is another component, sigma xy, which is the Hall part, which is essentially the fact that now that you have a magnetic field, and if you have current going here, you will feel some force, the charge will feel some force perpendicular to both. Therefore, there will be some current flowing also perpendicular to the electric field, and this is exactly what this is capturing. And sigma zz, which is parallel to the field, of course, there is no Lorentz force component. There is also no electric field. So, of course, there cannot be any conductivity, and this is just 0. By 0, I mean you can have at most this, but no effect of field, okay? And here in this, omega c is just the cyclotron frequency, which is EV over M. Now, again, 3 things that I want you to remember going ahead. First is the transverse conductivity, this is called the transverse, is something that decreases with the field, right? As field increases, this decreases. And this is easy to understand because as you increase the field, the particles will curve and it will travel longer before it can reach the end in the direction of the electric field, which means it will suffer more scattering, and this is what this is encapsulating. On the other hand, the Hall conductivity depends on the direction of the field. Why? Because of course, the Lorentz force will change if you change the direction of field. So this depends on the direction of the field and also is perpendicular to both field and the magnetic field and the electric field. And the longitudinal conductivity is independent of field. Now I put a star here. This classical statement can change even at the semi-classical level under certain situations. If you're interested, you can look up these papers, but we won't need it in this talk. Okay, so those 2 slides were purely classical ideas. Now you can ask, if I do an actual quantum calculation, does that hold true? So the way to do an actual quantum calculation would be simply to just use Kubo formula, which tells us that the real part of any conductivity tensor is simply proportional to the kernel to the susceptibility tensor, which is nothing but the correlation of the current. Okay, so it's just a current correlation. Now, if you want to calculate this, it's also not very difficult. For example, just electric field, you just calculate the single particle Green's function. this is your pole, and you just include the self-energy. Again, at the phenomenological level, you can use 1/tau, or if you want to do microscopics, calculate this and plug it in. But the idea is very simple. Once you have G, or for a non-zero magnetic field, you can again calculate the Green's function, same idea, except that now you'll have to go to the Landau level basis, and but the structure is similar. Okay, you have the Landau level wave functions, and you sum over all Landau levels. So once you have this Green's function, you calculate the current correlation function, and then that will immediately give you the conductivity. So for example, the classical ideas that I just showed you, the Drude part is nothing but the first simplest diagram in this, which is nothing but one bubble with the velocity vertices, which are the current vertices, because current is proportional to velocity. Of course, if you want to find real quantum corrections, which are beyond this, you have to consider higher order diagrams. For example, if you want to consider disorder with localization corrections, you have to consider all cross diagrams with disorder lines. And if you want to consider both electron and disorder together, which goes by the name of Altshuler-Aronoff corrections, you have to include both vortex corrections with disorder and your electron-electron interaction, which is the string. Okay. Once again, life is very simple for this talk for us, because I will be entirely devoting or concentrating on this level. There won't be any quantum corrections, which we will explicitly consider. Okay, good. So that was a sort of introduction. Are there any questions before I move on to the actual transport in Weyl semimetals?
Hi.
Yeah, hi.
Can I ask maybe fundamental question?
Yes, yes, please.
On when one consider a slice of in the k-space. So yeah, maybe you explained that in the Fermi arc part. So yeah, I sometimes confuse when how should I imagine if I consider the slice in the k-space. On the other hand, so yeah, I sometimes confuse on the correspondence to the real space. So could you tell me about the basic things which I should imagine when you consider the slice in the k-space?
Oh, you mean this part?
Yeah.
Oh, okay, okay. Yes, yes, I can. This will be much easier. So what I'm doing is, yes. So what I'm telling you is, in real space, you understand. So this is real space, right? Now in real space, I can calculate. So I can put a boundary condition instead of infinity. I just take a semi-infinite block, and I have a boundary condition here. Let's say hard wall. Then I can actually calculate the wave function as a function of this z in real space. But you see, the other two sides are still translationally invariant. So kx and ky are still good quantum numbers. Okay. So that means this state that I'm drawing in the 2D space, the kx and ky are still good quantum numbers. So that's your 2D k space. And the other side has become z. That's all I'm saying. Yeah. Okay. All right. Thanks.
Okay. Thank you.
Yeah. No problem. Okay, so let's now go to transport in bulk. I think I'm running out of time, so let me just rush a little bit. So here, of course, a lot of work has been done, so I'll just highlight the main ideas and give you certain references for other parts. Okay, so there are two sides to the story when it comes to Weyl semimetals and its transport in the bulk. Both are interesting, but the first part is non-topological, which is just electric field but not magnetic field. And the latter part is topological, which is once you introduce magnetic field. Now, what is so interesting about just electric field? You see, when I have a metal, it means that I have lots of carriers, as I just pointed out to you, in a partially filled band. If I have an insulator, there are two bands and the Fermi level is in the gap, there are no carriers. A Weyl semimetal, by very construction, forget about its spinor nature and everything, just the energetics of it tells us that if the Fermi level is right at the charge at the Weyl node, then you see it is somewhere between this case and this case, right? I mean, it's like a quantum critical scenario where you are just going from a metallic to an insulator situation. And you can then ask the question, which picture does hold if I just put an electric field? Now, as I argued before in a metal, the main idea is tau. And typically one can consider two kinds of microscopic relaxation mechanisms. The first is disorder, which is what I'm showing here as a red crosses, some impurities. And this is necessary to relax the momentum. As I said, as the electron is accelerated with E, these are the points where the electron hits and loses its momentum. So that is what gives rise to the steady state and gives rise to a residual resistivity at T equals 0. On top of that, I can also have electron-electron interaction, which is what I'm showing with a green arrow here, the interaction between the particles themselves. Now you see, under normal circumstances, this is an internal force, and they cannot really relax momentum, because once you put electric field, the electron gas as a whole will just come, the center of mass will just get accelerated. So in itself, it cannot relax momentum. It can only operate once there is some other degree of freedom, like disorder, helping you to relax the momentum, right? Of course, I'm talking about the normal circumstances. There are situations where it can also work, which goes by the name of Umklapp, but let us not get into that. I just want to focus on the normal electron-electron interaction, okay? And this typically operates at T not equal to 0. So that's my metallic picture. In an insulator, on the other hand, you see the main object is N, because to begin with, at 0 temperature, there is no carrier to begin with, so there is no conductivity. So at T not equal to 0, the only way that I can get conductivity is to excite some thermal carriers. And now you see, based on these two pictures, how this will be very non-trivial and doesn't really go with either of them. So let's consider the first case. I'm still at the limit of just root formula, sigma equals n squared tau over m. And I have my Fermi level at the charge neutrality, meaning there are no charge carriers at T equals 0. But now let's say I have an electron-electron interaction, and I turn on some temperature. Now you see, the moment I turn on temperature, it will immediately excite some particle-hole pairs, right? And that is unavoidable. Any perturbation will do that because my Fermi level is here. And now you see, unlike the metallic case, once I have a particle-hole pair, and because of the spectrum, they are exactly at same energy and same momentum. Just having one is hole and one is electron. So under the electric field, one will go to the right and one will go to the left. So it doesn't matter how much electric field you put, the net momentum of the system will always be 0, which means that in this case, you really do not need anything else to relax your momentum. Just electron-electron interaction will suffice to give you a finite conductivity. And this is exactly what this calculation is telling us. Let us not go into the details of the calculation, how this scaling is different from a standard Fermi liquid. If you're interested, I can come back to this later, what these terms mean. But essentially, all this means is that this is the Fermi velocity, which is renormalized by the fine structure constant, effective fine structure constant here, and lambda is some ultraviolet cutoff. But the basic idea is this. This is fundamentally different from what you would get in a standard metal. The same idea carries over to disorder. As I said, that now let's say we have just disorder and no electron-electron interaction. Again, as I said, you don't need any temperature. You just put any perturbation, the basic fluctuation due to any perturbation, because this can be thought as a quantum critical point, will immediately create some electron-hole pairs. That means, although n is 0, the very scattering method that you are putting into the system will also create your carriers in some sense, and it will give you a finite conductivity, and which is what this expression says. Okay, so as you can see, there is no external n here. It's all fundamental constants times the Fermi velocity, which is sort of giving you an effective n. The gamma here is proportional to 1 over tau d, an effective disorder scattering time, and that is your sigma here. Okay. Again, there is more to this story. There are other regimes where this result might change depending on how you take appropriate limits. But the essential idea is this, and you can certainly go into this these references if you're interested in more. Okay, let's now turn on the magnetic field. Now, this is where topology really kicks in a Weyl semimetal. Now, we have all heard about Chiron anomaly over the last 2 or 3 days in different ways. I'm going to give you 3 different alternative ways of understanding Chiron anomaly from different perspectives. Depending on your background, your preparation, and depending on what you want to calculate, you will, I'm sure, find one of this more conducive to your way of thought. So let's start with the simplest way, which even an undergraduate student can understand. So I have a Weyl semimetal, let's say with 2 valleys, that is 2 chiral nodes. and I apply a field, no electric field, just a magnetic field. Well, basic quantum mechanics tells us that I'll immediately have Landau levels, right? Now it turns out that all the Landau levels which has n plus minus 1 plus minus 2 will have this form, except that is they will disperse like this along kz, because this is a three-dimensional system. Only two dimensionals will have the Landau level index, and the kz part parallel to B will disperse, and this is what I'm showing here. But the 0th one will disperse chirally, meaning on one side it will go straight down without changing its slope, and on the other side it will just go straight up without changing its slope, right? And now let's do a very simple calculation, which is after I have applied the magnetic field and I have chiral, the Landau levels, for all practical purpose, this is just a one-dimensional system with dispersing bands in one dimension. So if I think how the charges are moving out with time because of my electric field, I can simply think that the rate of change of charge with time is how many points there are in the K space. We know K is in terms of 2 pi over Lz. Lz is the dimension, real space dimension this side, that over delta t, right? Okay, and that is essentially Kz dot. Now, because there is an electric field, this Kz change in time according to the force in this electric field. So I can just plug it back in, and this tells me that the rate of change of one-dimensional band, this charge at each of the nodes is essentially just chi times Ez times Lz. Lz is the system size on this side. Now, I need to go from one dimension to three dimensions. How do I go? Well, it's very simple. Each Landau level we know has a high degeneracy, and the degeneracy is proportional to the field itself times the area. Area meaning the other two dimensions of the sample, so that the total volume is simply AXY times Lz. Now, once to get the three-dimensional charge current, I have to just take this one dimension and just multiply with the degeneracy, and immediately you see that this Ez multiplies with Bz, giving you a E dot B term. The chi stays as it is, the volume stays as it is, and you have some prefactors. And this is what exactly a Chiron anomaly is, which tells you that under parallel electric and magnetic fields, the charge is not conserved in each valley separately. It's only total which will be conserved. Okay, the next way to understand this is from field theory, which is I can simply write down a partition function as a path integral. This is the action. And let me start with the action for, again, two Weyl nodes of opposite chirality. So this is my standard action. And this B mu here, the space-like part is essentially the momentum separation in the two Weyl nodes. And the time-like part of this is just the difference between the chemical potentials, right? And let's now do a transformation, a chiral transformation, which takes psi to another psi through this chiral transformation, right? Now, if you do that, you see, by the way, so B mu x mu here, which is, I'm terming it as theta x in this exponent here, is nothing but the B dot R in the space part and B naught T in the time part, okay? Now, observe that once you do this, transformation, your entire B mu is gauged out. So this action just goes to the standard Dirac action, which is massless. So then one would think, oh, then probably this has no meaning because I have just gauged out. So the Noether's current would be conserved in each valley. There is no meaning of having a separated Weyl, right? However, the problem is that it is not just this which one should look at. It is also the measure of the integral. And if you do it properly, then you can show that the measure of integral under this transformation accumulates a Jacobian. And it turns out that this Jacobian actually accrues a non-trivial exponent in terms of the electromagnetic tensor, field tensor, okay, where this theta x has the information about the separation in energy and momentum. Okay, so that means once you plug this in and then here in your original partition function, you see that you do get an extra term in your action, which is exactly like an axion term. That's why I'm writing this as theta, except that this theta is now linearly dependent on space and mu, the time component. And once you have that, it tells you that the corresponding Noether's current which is your chiral current or the axial current, is not conserved anymore, but just this. And this is exactly the E dot B that we just saw in the last one. Okay, the final slide is the same chiral anomaly from semi-classics. So why am I showing you this? You see, in this slide, in the first slide, to understand chiral anomaly, we explicitly need to know about the Landau levels. And you might come to the conclusion that this is purely a phenomenon that needs you to go to the ultra-quantum limit, because it is only the 0th Landau level phenomenon. On the other hand, this picture has no Landau level at all. It gives you an impression that this should occur at any field. There is no criterion on the size of the field here. And also, in these two pictures, I have not made any explicit reference to the topology, the way I described it, which is through the Berry curvature and the Berry flux. So how does one connect all these pictures? And this is where the semi-classical picture becomes very useful, where you essentially just write down the Boltzmann equation, which is a quasi-classical thing. So you think of a distribution function in momentum, position, and time space. And you just say that the total rate of change of this with time is equal to whatever the scattering that could happen in a volume element in your phase space, and that could kick the particles out, right? This is something that we do in statistical mechanics all the time. So there's nothing new here. What is new though is that what are these r dot and k dot? Now, in an ordinary material, the r dot is nothing but the velocity that you get from your band, del E, del K. And the k dot, which is the force, is essentially the electric field and the magnetic field, Lorentz force. That is ordinarily. Now, the new part that has entered in any object, so this has got nothing to do with Weyl. Any band structure, any material that has a very curvature associated with the momentum space will get an additional contribution for this r dot. Okay, and so does the density. So if you don't have this, the density is just delta ek minus e integrated over all volume and momentum space. But in presence of this, there is a correction. Okay. Now, what does this mean? You see, this term and this term are very similar, which means that as in real space, the Lorentz force acts as if not as if, the Lorentz force is essentially the magnetic field operating on the real space velocity. The Berry curvature essentially acts as a similar magnetic field, but in the k space, which acts on the velocity in the k space. That is what this is telling. And also this has made life slightly more complicated because these are now coupled equations. So k dot has to be put there and r dot has to be put there. So one has to solve consistently. So let's first go very simple. Let's assume that there is no spatial dependence in our distribution function. So let's put this term to 0 and let's suppose that there is no scattering at all. Okay, so if I put an electric field, it will just dart off to infinity. In this case, you can just take this expression, integrate over all volume in the momentum space with this density of states, and you can immediately show that at each value, which I'm denoting by j, the continuity equation is not valid. It just gets broken by the term E dot B, which is exactly what we had encountered before. Okay, and this chi here is the same Berry flux or the monopole charge that we had defined, right? So now you can immediately see that the charge is not conserved separately in each value, but if I sum up all the j's, this and this, immediately the right hand side will go to 0 and the total charge will be conserved. Okay, very nice. So I have given you 3 different ways to understand chiral anomaly, and now I will tell you how this chiral anomaly manifests in anomalous properties in transport. Okay, I really need to hurry up. So let me just go along with the picture and the semi-classics itself. So if you just go back and put some scattering form, again phenomenologically some tau, and keep your thing space independent, then you can immediately show that the current is this term with the distribution function, and the distribution function in turn is the equilibrium part plus some correction, which is up to linear ordering electric field, because we are in linear response regime. And now it's just a matter of matching. So as you can immediately see, if your omegas are 0, Berry is 0, all these go to 0, and the only term is your Drude part. This B couples with this B, and it will give you exactly the Drude part we discussed before. Now, if you consider this equilibrium with this part, you will get something called an anomalous Hall effect. If you couple this with this, you will get something called the chiral magnetic effect. And if you couple this with this, you will get something called a nonlinear magnetoresistance. By the way, all this can also be derived in the other two methods. For example, here you can just take this action and just take one derivative with respect to the field. You'll immediately get those anomalous features. Okay. All right. Very quickly, what do these things mean? So the anomalous Hall effect is essentially, you can see it's coming from a scenario where the current is perpendicular to both electric field and the Berry curvature. Just like our old Hall effect, except that instead of a magnetic field, there is no magnetic field here. It's this omega, the Berry curvature, which is playing the role of a field. That's why this is called an anomalous Hall effect. The chiral magnetic effect is that the J, the total current summed over all the nodes, actually does not even depend on the electric field. It's just proportional to the field. And you see that if the mu's, which is the chemical potentials here, are same, then of course chi j summed over will give you 0 and won't give you current. But if there is a difference in the chemical potential, it will not give you 0. And finally, the idea of negative longitudinal magnetoresistance, which has received perhaps the most amount of attention in condensed matter, says that you just calculate the sigma zz, this term and this term. You can see the omegas are squared, so there is no more information about the sign of omega, and b is squared, which means this is a conductivity that increases with the magnetic field in the direction of field. And now, if you remember our introductory part, I had told you that in a normal metal, in the direction of the field, there can never be dependence on the field because Lorentz force is 0. And even if there was, conductivity can only decrease with the field because it has to traverse more path. But here you see exactly the opposite. There is a conductivity which depends on the field in the direction of the field, and it is actually increasing. That is, the resistivity is decreasing. This is an experiment where it actually shows you that the resistivity does decrease when your fields are aligned together, but as you go perpendicular, it goes back to the ordinary scenario. Okay, if you are interested in other features, there are a host of other features. You can just have a look at these excellent references, which are all reviews on the transport features. Okay, very quickly now, let me actually go to the main part, which is the work that I've been doing over the last couple of years, and which is transport on the surface of a Weyl semimetal. Now you see, we have encountered a host of features in the bulk of our Weyl semimetal. One can definitely ask the question, are there similar anomalous properties right on the surface? I can always imagine that I just put a battery on the top and just measure the current, just DC transport, right? Now you see immediately there is an issue here. It's slightly more complicated than before, because as I told you, on the surface, the state that lies in the Fermi arc, it is intrinsically leaking into the bulk. There is no scale on which you can separate it out from the bulk, which means that there is no way that I can write down a surface Hamiltonian purely as my starting point and then turn the machinery on. Any response on the surface must be intrinsically connected to the bulk. Okay, but still it's a well-posed question. We can ask, what is the response on the surface? Now, to circumvent this problem, what we're going to do is the following. We're going to use a layered model of a Weyl semimetal. The model is as follows. We stack up alternate layers of electron and hole. Okay, so xi k here is just some dispersion and some number here. So this equal to 0 gives me a Fermi surface of electron, and minus of this gives me a hole. And I'm just coupling them one after another. And the interlayer coupling is essentially two kinds. Let's call them minus tk and minus delta k, some function of k. So k here is just the in-plane momentum, because this out of plane is the real space z. Okay. Now, the only stipulation that I'm making is, so your dispersion can be anything here. The only stipulation I'm making is that these can also be anything, except that the difference of these two quantities must change sign at certain discrete points called kj, kj being the in-plane momentum. Okay. So this should go to 0 at certain discrete number of points, and then it should change sign. Now, my claim is that if you have such a Hamiltonian, then in the bulk, it will actually give you Weyl nodes at these kj points. And on the surface, it will exactly give you the Fermi arcs that I have talked about. So let's quickly verify that. So first, let's take our layer description and make it infinity on this side as well, so that this is also a good quantum number in momentum. Then I can write down the bulk Hamiltonian, all in 3D k space. And at the points where xi k and this tk minus delta k goes to 0, that is on these lines, and on the points where delta k equals tk, you can show that this Hamiltonian immediately reduces to a Weyl form that I had shown you earlier with anisotropic velocities in general. Okay, the sigma here, the Pauli matrices, as I said, it's a pseudo-spin degree of freedom which matches our layer degree of freedom, the electron and hole here. Okay, these velocities here are nothing but the gradient of the parameters we have used. So grad of Ek, this is the gradient of the two interlayer couplings, and this is just the out of plane coupling Tk. Now, that is one part of the story. If you actually calculate the chi, the monopole charge at these Weyl nodes, you can show that it has the sign of this particular velocity along the tangent on these lines. Now, as I had told you, by construction, this quantity will continuously change sign at each kj point, which means this by construction is guaranteed to alternate signs, meaning we'll always have even number of Weyl nodes satisfying Nielsen-Nienomiya theorem. So the bulk is checked out. Let's go to the surface now. We also need to ensure that this gives us the right Fermi arc. Now for the surface, now we consider a semi-infinite stack of slabs. At this point, now for this semi-infinite scenario, it turns out that you can calculate the surface Green's function, by which I mean the g of z equals 1 as a function of your in-plane momentum. And this is an exact expression. So it turns out that this surface Green's function has a standard pole that we always encounter in a free Green's function, but with certain numerators. And the numerator expressions are given here. And these two factors in the numerator are actually very important because this is what actually gives us the Fermi arc. Why? Just think about going to the pole. Okay, so on mass shell, you put E equals Ik. At the pole, the moment I put E equals Ik here, this gives me Tk square minus delta K square. And here, this cancels out, I have mod of Tk square minus delta K square. And now you immediately see that this is non-zero only when Tk is greater than delta K, but immediately goes to 0 when Tk is less than delta K. And this is exactly what a Fermi arc is, right? Here, it has to appear only on a certain segment on the surface, as long as Tk has some relation with delta K. And this is exactly what we have found out. The Green's function will go to 0 in the other sector. So there are no states on that sector. Okay, so non-zero only on the Fermi arc. So that checks out as well. Very good. So now let's calculate surface conductivity with our Green's function. As promised, I'll do the simplest possible calculation, the Drude part. And I'm just essentially just doing the GRGA with the Fermi function derivative. Okay. All right. This is my Green's function that I had just shown you. Now this I have just rewritten as factors, this part here, to explain to you that this means that this Green's function has a branch cut on the imaginary or the complex energy plane, right? There are 4 factors. It tells us that the Green's function will have 2 branch cuts. These are the 4 branch points. And accordingly, I can split this energy integral of my otherwise standard calculation into a normal region where there are no branch cuts and a region which has the branch cuts, right? And I am working in the limit where disorder is very small. So 1 over tau goes to 0. Now you see that in the limit that temperature is small, this is my cartoon of the Fermi function distribution. This part, this other branch point, xi k plus tk, as long as t is much less than the coupling parameter here, t naught, these points will hardly contribute to my integral. So I can just extend this to infinity. And accordingly, instead of having 3 normal regions, I can think of this entire domain as a branch cut, a normal region and a branch cut, right? Okay, so that's the only little part more than my usual standard metal calculation in this case. So let's now do the normal region. If you calculate in the normal region, let's go to t equals 0, then the Fermi function is just a delta function. All your contribution comes from just the normal region, and immediately you can show that the conductivity is nothing but the standard Drude conductivity coming out of this entire Fermi arc, except with the difference that there is in this velocity average, there is a factor 1 minus delta k square tk square. Now that makes sense because, as I told you, At the Weyl nodes K1 and K2, delta K is equal to Tk. That's by definition, which means this factor goes to 0. And that makes sense because, as I told you, on the surface, this state is leaking into the bulk. So strictly on the surface in the Weyl node, there is hardly any weight. So this term completely goes to 0 and contributes much less or 0 to the Drude conductivity than somewhere in the middle of the Fermi arc where this is the maximum. Okay, that makes perfect sense. Now let's go to the other side.
You have 5 minutes left. Yeah.
Yes. So the other side is the branch cut region, which now comes from here. And you can immediately see that if I don't have a finite temperature, this branch cut will not contribute because it can only come from this part of the energy integral, right? So I introduce a finite temperature. And the moment I do that, you can immediately see that the dominant contribution comes from the edge of the branch cuts. And you can see the edge is defined by xi k and tk minus delta k. That means we are getting a dominant contribution from the region xi k equals tk minus delta k equals 0. But as I had told you, this is exactly the region which is by definition the Weyl node, right? That means this part is encapsulating or capturing the contribution from the Weyl node. And if you carry out this calculation, you can see that it goes as t squared. With some velocity squared, where these velocities are no longer the average, but the velocity that is appearing just at the Weyl nodes. That's what this index is. The most interesting part of this result is that you see there is nowhere tau that appears in this expression. This expression is completely independent of the scattering time, okay, which is very unusual because how can conductivity be independent of the scattering time? Okay, let me not belabor the point. I'm running out of time. So if you do it for non-zero mu, that is, you are not at the Weyl point, but slightly above, you can do the same thing. You'll get a very similar expression with no scattering time dependence at all, right? Okay. Now, so far, the surface conductivity that I've calculated only consists of terms that entirely depends on the surface. In principle, there are other processes which will go through the other layers, but let me now make an approximation where I say that this coupling is much smaller than this. So we are in the layered approximation, and let me throw out all these terms. So what I've calculated so far then can be thought of as the right result in the layered Weyl semimetal approximation. Okay, good. So I have my final result now. The result tells me that in a layered Weyl semimetal surface, the surface conductivity not only has a regular Drude part which comes from the entire Fermi arc, it also has an anomalous part which comes only from the Weyl nodes. And this is anomalous because it is completely independent of your scattering time tau, and whose role instead is now played by 1 over the interlayer coupling. Also, you can see that the temperature dependence now of the conductivity is increasing with temperature, which means if I plot the resistivity, which is inverse, should decrease with temperature. And this is what I'm showing you as a cartoon. If you remember, in our standard metal, resistivity should always increase with temperature. And this would always also hold true here if you include your temperature dependence in tau. But if we go to sufficiently low temperature, such that this temperature dependence is overwhelmed by this temperature, it tells us that as a clear signature in experiment, one should see an upturn which scales as t squared. This is the concrete prediction that we are making. Of course, below certain temperature TQ, quantum corrections should be important. So we don't know what will happen there. That requires more work. Okay. All right. Now, as an interpretation, I have 2 more minutes left. So I'll just tell you very quickly. So what is the origin of this extra anomalous part that we're getting? Instead of going through the calculation, I'll just tell you, you can show by calculating the surface density from the branch cut part that essentially what this extra carrier is nothing but it is excitation from the bulk itself. Okay, and because the Weyl part leaks into the bulk the most, that's the region which is contributing dominantly. So that is the origin of the anomalous part. But what is most interesting, and which I hope Sayantan, just give me a couple of minutes extra, I'm sorry. But this is, I think, the most interesting part of this talk is that why there is no dependence on tau. How can we have finite conductivity without tau in this anomalous part? And to understand that, let's go back to the original Green's function that I wrote for the surface. Now, you knew, I showed you that this Green's function in this region, in a certain region in the energy space, has branch cuts, meaning the Green's function not only is real, but also imaginary. Note that I have not put any self-energy here. This is a perfectly free Green's function. This imaginary part in this energy domain, I can easily rearrange to give it a form of an interacting Green's function, where the numerator is the standard quasi-particle residue. And this is our self-energy, something which we routinely encounter, for example, let's say in a Fermi liquid, right? Now, in this case, even without putting any self-energy by hand in this domain, because it becomes imaginary, I do have an effective quasi-particle residue in terms of this G1, G2, and an effective self-energy, which is proportional to E minus xi k. Now, you see, what does this tell us? What it's telling us is that as long as we consider processes which involve electrons which are off mass shell, there is no way the surface immediately will behave inherently as a correlated liquid. And this correlation is purely a result of the scattering from the bulk, which we have ended up capturing in our theory. Okay. All right, I can skip this. So let's go to the final conclusion. So what I've showed you is that the electromagnetic response of Weyl semimetals has numerous anomalous behaviors. In the bulk, there are two origins. One is simply because of the interesting band structure, and this is largely non-topological. And one is because of the topology, which results in Chiron anomaly, and this is in the presence of both electric and magnetic field. And what I've shown you something new from our own work is that on the surface, we do have interesting anomalous response, which is in addition to the Drude response from the Fermi arc, there is an anomalous part which arises from the intrinsic surface bulk connection and is completely independent of surface disorder, at least when disorder is very weak. Okay, what lies ahead? Well, it's essentially now, I think the picture is pretty clear. We want to understand both transport and new phases on the surface, including both the interplay between this intrinsic correlation from the bulk and explicit interactions that we usually encounter in our condensed matter systems. Okay, so I would like to acknowledge help from my collaborators, Pavan Husur at the University of Houston and his graduate student, Eki, financial support in the form of startup grant from IIT Bombay, and we are in the final stages of preparing the manuscript. So hopefully it will come out within the end of this month. So if you're interested, please look it up. Thank you very much, and I would love to have some questions. Thank you.
Thanks for this great talk. And we have a question. Pavlo, please kindly unmute and ask, please.
Hello, thank you very much for the talk. So
Yes.
I'm a little bit confused regarding the part of the surface transfer, related to the surface
Yes.
transfer. So you notice that in principle, it's possible to have a Drude part of the Fermi arc transfer.
Yes.
But if you consider the simplest case, let's say Strain's Fermi arc, so this would correspond to a one-dimensional state. But in the case of one-dimensional state, it's possible to solve this equation precisely, and in this case, disorder will just drop out. So there should be no Drude part in this case.
Right.
Why is it appears in your case?
Right. I understand your question. So there are two aspects to it. First, by construction, this is a spinless system, which means it has time reversal broken symmetry. So, which means that you are allowed to scatter from one Fermi arc to another segment of the Fermi arc on your surface. That's first. And the second part of the answer is that in your usual toy models that one considers to get the Fermi arc, here. This is a straight line. This has dispersion only along one direction, right? In the literature, that's what it's done. In our case, because this is appearing from this xi k, it is essentially you have full dispersion in kx and ky around 2 dimensions, which you are gapping out by this coupling at some point. So this is really, it is a part of a 2D Fermi surface. It's not really 1D. So it is possible to scatter from one side to another. between two different points. So it's not a one-dimensional dispersion object.
It's still a chiral state. It cannot be true.
No, so
Curvature doesn't matter.
Yes, so the chiral state. So the point is that you, in your expression, that comes from your absence of backscattering from the wave function. This is what you mean, right?
Yep.
And so if it is a strictly 1D system, then and you constrict all backscattering, then of course you cannot have any root part. But in general, that is not the case, right? We do allow scattering from one part of the segment to another. So in this model, at least, you can always have a root part. That is the reason.
So, so is it somewhat related to the fact that you still have some bulk scattering to the bulk, or what?
No, so the root part is not coming from the bulk scattering. It is the other part that I discussed, which is coming from the bulk. The root is really just from the 2D Fermi arc state. Yeah.
Okay, sounds a little bit strange, but
Okay, thanks. So I would request to follow this up discussion in the Slack channel, and I guess we should go ahead.
Okay.
Igor, thanks, Hridish, for this excellent talk.